Welcome to The Explainer. Today, we're jumping into some seriously big ideas in physics. We're going to break down work, energy, and, uncover the one law that pretty much rules the entire universe.
Okay, so let's just dive right in. What in the world connects a flying baseball, a stretched-out spring, and, well, everything? It kind of sounds like a riddle, doesn't it? But the answer is this single, incredibly powerful concept, energy. And to really get our heads around energy, we have to start with what physicists mean when they say work.
You know, in our everyday lives, we talk about working hard all the time. But here's the thing. You might be surprised to hear that in physics, the word work has a very, very specific and maybe even a little strange definition.
So in physics, work is all about energy transfer. But here's the catch. It only counts as work if a force, a push or a pull, actually causes something to move. That's the absolute key. You need both ingredients, a force and some movement in the direction of that force. No movement, no work. Simple as that.
And this is where it gets interesting. Pushing a shopping cart, lifting a heavy box, yep, that's scientific work. A force is causing motion. But what about holding a super heavy weight? Just holding it still. I mean, your muscles are burning, it feels like the hardest work imaginable, right? But because that weight isn't actually moving, you're doing zero scientific work on the weight. Your body's doing all sorts of stuff internally, sure, but the weight itself isn't going anywhere.
And that brings us to this idea of null work. It means exactly what it sounds like. You could push against a solid brick wall with every ounce of your strength, but if that wall doesn't budge, the work you've done on the wall is a big, fat zero. Force without motion equals null work. It's a fundamental rule of the game. But what if the force isn't steady? Like when you're stretching a spring, it gets harder the more you pull. So how do physicists handle that? Well, they get visual. If you plot a graph of the force versus the distance, the work you did is simply the area underneath that line. The fancy term for this is an integral, but really, just think of it as a clever way to add up all your effort over the whole distance.
Okay, so if work is about transferring energy, then power is all about how fast you do it. See, lifting a box onto a shelf is the same amount of work, whether you do it in 1 second or 10 seconds. But doing it in 1 second, that takes way more power. Power is the speed of work.
All right, so we've established that work is this force causing motion. But what's the actual result of that work? What does it create? Well, that brings us right to the energy of motion itself, and that is kinetic energy. It's the energy something has just because it's moving. A car speeding down the highway has it, a planet orbiting the sun has it, you have it when you run for the bus. And the faster you go, or the heavier you are, the more kinetic energy you're packing. Now, here's the beautiful aha moment. This is how work and energy are locked together. It's called the work-energy theorem, and it's so elegant. It just says that when you do work on an object, you are directly changing its kinetic energy. The work you do doesn't just vanish, it gets perfectly converted into that object's energy of motion. It's a direct deposit into its energy bank account. But hold on. Energy isn't always about things whizzing around, is it? It can also be stored, waiting. This is all about the power that comes from an object's position.
Now, this is super important. Not all forces are created equal. First, you have what we call conservative forces, like gravity. If you do work against gravity by lifting a book, gravity kindly stores that energy for you. When you let go, it gives all that energy right back as motion. It doesn't care how you lifted it. Then you have the other kind, non-conservative forces, like friction. When you slide a box across the floor, friction turns that energy into heat, and you can't get it back. The energy is basically lost from the system. And that stored energy? We call that potential energy. An object has it because of where it is or how it's configured. And here's the really crucial part. You only get potential energy from those conservative forces, the ones that are nice enough to give the energy back. It's energy that has the potential to become motion.
So let's make this real for a second. That book sitting on a high shelf, it's loaded with gravitational potential energy because of its height. A stretched-out rubber band pulled taut, that's packed with elastic potential energy. In both cases, there's a bunch of energy just sitting there, stored up, waiting for a chance to be released.
So what happens when you add it all up? When you take the energy of motion, the kinetic, and you add it to the stored energy of position, the potential, well, you get what we call the total mechanical energy. It's the whole shebang, what's moving plus what's waiting to move.
And this is where it gets really beautiful. In a perfect, isolated system, one with no friction, no air resistance, just nice, conservative forces like gravity, that total mechanical energy never changes. It's conserved. Think of a pendulum swinging back and forth. At the very top of its swing, it's all potential energy. At the bottom, it's all kinetic. The energy just transforms back and forth, but the total amount stays exactly the same.
Okay, but let's be honest, that's a perfect world scenario. The real world has friction. It has air resistance. So what happens to our neat little law when it collides with reality? This brings us to the final and truly unbreakable law of energy.
Yeah, this is the big question, isn't it? We've all seen it. A bouncing ball eventually stops bouncing. A pendulum eventually stops swinging. That mechanical energy seems to just disappear. So where does it go? Is it just lost forever?
Well, the answer lies in those pesky non-conservative forces, which have a formal name, dissipative forces. They're called that because they seem to dissipate or get rid of mechanical energy. Think about it. Rub your hands together really fast. The work you're doing against friction doesn't make your hands fly apart. It makes them warm. The energy has been converted into heat.
And there it is, the big secret. The energy is never ever lost. It's just transformed. All that mechanical energy that seems to vanish from a bouncing ball or a swinging pendulum, it's perfectly accounted for. It's been turned into other forms, mostly the internal energy of the system, which we usually feel as heat. Nothing is lost. It just changed its costume.
And all of this leads us to one of the most powerful, most fundamental rules in all of science, the principle of conservation of energy. You cannot make energy from scratch, and you cannot destroy it. All you can ever do is change it from one form to another, from potential to kinetic to thermal to chemical, and on and on. The total amount of energy in a closed system, like our entire universe, is constant. It never changes, period.
So let's end with this thought. If every single thing that happens, every star that burns, every wave that crashes, every thought in your head, is just energy changing form, and if the total amount of that energy is fixed, what does that really mean for the future? For the direction of time itself, and the ultimate fate of the cosmos? That's the mind-bending implication of this one, single, unbreakable law. Thanks for joining this explainer.